First, Sci-Fi 2012 is going to be Scott.Livingston talking about TuLiP, tool for hybrid and reactive system research.
Testing? Okay, good. So thanks again for the introduction. One moment while I orient myself. So again, my name is Scott.Livingston. I'm a graduate student at Caltech, advised by Professors Murray and Burdick there. And before I begin the talk, I want to give a meta-level comment. So just to give you a perspective on my perspective, this is my first time to a sci-fi conference, and most talks seem to be from people who do research in physical science, and my research broadly can be associated with or put under the umbrella of motion planning in robotics. And so I'm interested not just in using the scientific Python stack to analyze data, so for exploratory analysis, for modeling and visualization. I'm also interested in using it for quick prototyping of algorithmic ideas. So I don't know what everyone's background is, it's a broad audience, but that's just to give you my perspective. So I use it not only for data analysis, but also for quick prototyping for engineering research questions. So on to the talk. This talk is about TuLiP, TLP, with gratuitous use of capitalization. TLP stands for Temporal Logic Planning. Hopefully you'll have some idea what that means toward the end of the talk. And there's a subtitle, Toolbox for Hybrid and Reactive Systems Research. So I say contributors because there are other people who have contributed, but too many names to list. Let's see if I can get this. So quick outline, I'll spend some time on background. That's just to orient everyone. Again, I assume very diverse backgrounds, possibly a limited representation from those conducting research and engineering related disciplines. And then I'll talk about the toolbox itself and a couple modules that are more of general interest. So my specific target audience is the target audience would be hybrid systems researchers. And this is supposed to be a framework for that, as I'll talk about, but there's some modules that I think would be of interest outside that discipline, and so I'll mention them there. And then I'll make some design comments just as a view of the development process itself, and then close with acknowledgements. So, know your roots. This began as an implementation for a particular method proposed by Wang Pramsarn, PhD at Caltech in August 2010. Actually, she defended in May 2010 and then kicked out the Python code in August. And so that turned into a paper, a so-called tool paper at a major hybrid systems conference, HSCC, Hybrid Systems Computation and Control. And those are some of the people associated with it. And that's really where it began. So really, at that point, it was just a particular algorithm implemented in some Python code. And at that point, it certainly did not have all the structure it has today that I'll talk more about, but it had a dependency on MATLAB that was crucial. So an important computation that's a part of this implementation is on what are called polytopes. I'll roughly sketch them out later. And that depended on the multi-parametric toolbox, which is more like a conglomeration of toolboxes for MATLAB and includes optimization routines, which we also need, and polytope routines as well. And there were at least two problems with that. First, I hate MATLAB, and I don't think I need to make that point here too much. The issue is reproducibility and collaboration and so on. And there was another issue, which was licensing. Some of the code in NPT was not open source, and enough said on that. TuLiP is in Python. It's in a BSD style license, so I'll give you the URL at the end of the talk. And just to mention quickly that the current use of it is as a framework for hybrid systems research, in particular robotics, but really more general notions of hybrid systems. Mostly in RichardM.Murray's group at Caltech. We have some collaborators who are beginning to use it at Berkeley, and some people who we've never had contact with before are contacting us about it. So it's beginning to grow. Still a very young project. Like I said, it began in August 2010. Really, the development didn't take off in its current form until second quarter of 2011. Okay, so we'll talk about some background. I'm just going to sketch this out intuitively just to give you a context to understand the tool. If you can approach me after the talk, and I can go into much greater theoretical detail if you're interested on precise formulations. And as a high-level comment, compared to the previous talk, I'm not going to spend a lot of time on the API itself. I will look at some code later, but really what I'm trying to do is motivate you to see why this is an interesting tool, why it might be useful for your research, even if you're not in hybrid systems, but if you are, then it is also great in that context. So dynamical system. I suspect most people have come across the notion of a system. Basically, it's a black box, and you have some kind of sequence of inputs coming in, and some sequence of outputs going out, and that's it. That's a system, a systems level view of the world. And from a control theory context, what we're trying to do is take some kind of system that's a plant, and the term comes from a historical chemical plant control kind of problem, and we're trying to construct a controller C that will get the plant to do something interesting, something that we want. A concrete example would be you have a UAV that you're trying to fly, and the UAV is P, it's the plant you're trying to control. You're trying to get it to follow a reference trajectory, and with C, you have, for example, a flight controller that will cause the UAV to fly along its course stably that you commanded despite external perturbations. It might be unpredictable. So the specific type of specific type of dynamical system that TuLiP looks at is a discrete time. So there's some F that describes how your current state, Z, and a control input applied at that time, U, map to a next state, ZK plus 1. So K is this index of discrete time. And by the way, you can interrupt with questions. I know that hasn't been the basic paradigm of the conference, but if you're really lost and it's epic and you want to elaborate a bit, we can do it. So, but that's it, discrete time system. So another type of system is a so-called reactive system. Now, whereas the previous dynamical system historically was a concept developed in a control theoretic, electrical engineering crowd, telecommunications historically, missile guidance. Reactive systems is a computer science notion, a theoretical computer science. So currently, if you were interested in looking at work on this, you would search for the keywords computer-aided verification. And so what is a reactive system? It's an interactive, non-terminating program. And you can be more theoretically formal about it. This is in contrast to quicksort, for example, which is a so-called transformational program, or your basic notion of an algorithm which takes some input, does some kind of work on it, and then gives you something back and terminates. Reactive programs are always running, so they're really a paradigm for modern services that are just on the web, for example. So reactive systems typically are defined to have some kind of desired behavior, and the two basic kinds are safety properties, which are things that must always be true, and liveness properties, which are things that should be eventually true. And a concrete example is a web server, and so a web server is always on. We never want it to stop, so it's not transforming data, it's just something that's serving clients unpredictably in the sense that you don't know when a client will arrive and request something. A safety property in that case would be always respecting the appropriate rights that users have. So someone should not get root level access if they didn't provide proper authentication. And a liveness property in that context would be if I want to see the Wikipedia homepage, or if I want to see this particular web page, and I submit that request to the server, my request should eventually be served in finite time, or I should get some kind of message back that says it's not possible, but I shouldn't just be left hanging. And so two basic questions you can ask about reactive systems are they correct? So here's a system, here's a web server, a piece of software, here's a formal description of what it should do, a formal specification given in some kind of formalism like temporal logic that we won't define more. And verification asks, does the system meet that specification? Synthesis asks, given a formal description of what we want to do, is there an automatic way to construct a solution? In this case, we're looking at finite automata solutions. So how can we connect these two pieces together to form a particular class of hybrid systems? We can use what's called a discrete abstraction. So fairly quickly, toward the top of the slide, we have that discrete time system again. And in the middle, we have some kind of room. So let's start talking about robots, which I claimed, even though I say hybrid systems research is the target of this tool, my research is mostly in robotics. So here's some room. There's a door to the lower left, and we're trying to get the robot to do some kind of behavior. Like let's say there's a trash can in the bottom right. We want the robot to go in there and pick up the trash. So how would we map this continuous space, this rectangle, subset of the plane, to some kind of finite representation where we can apply methods from reactive systems to it? And one way you can do that is to define a decomposition of the space into finite many components and label them. So the first thing you should quickly notice is I mentioned the trash cans in the lower right, so there's a small cell there. And roughly, when you select a partition like this, you should select it to reflect the task. So it's motivated by a high-level description of what you want the robot to do. And you should also satisfy a property called reachability. And roughly speaking, what it means is you've broken up the space into these finitely many cells. And so, for example, after doing that, you can ask, if I'm in cell 1, can I get to cell 4? Is there some kind of control law that can drive the robot, apply torque to the wheels, and move it there reliably? And if you can do that, then you can say that cell 4 is reachable from cell 1. And if you extend this to other cells, you can actually then get this sort of transitivity property among them. And long story short, you get a finite graph out, which means now you can study the problem of forming some kind of behavior over the space with a finite representation like a graph, solve a graph planning problem, and then map it back down to the continuous space by implementing it with the specific control laws. And so we're almost done with background. And this is the motivating problem that TuLiP is designed around. I won't talk too much about the classes in it, but there are classes specific to, for example, representing a temporal logic formula that describes the kind of behavior that you want to be performed in the space. So what we had was an office floor plan, and we had broken it up into regions of interest. This is regions of interest at the level of the task. So we're going to assume the hallway is always eventually free, and then if we can make that assumption, if it is in fact the case, then we want the vehicle to drive to room Q in the upper right, and while it's doing that, we want it to avoid collisions. So this is just a temporal logic statement of that desired task. And then when we incorporate the dynamics, we then refine the partition in order to meet that reachability property. And so in TuLiP, there is a Python class for representing specifications like this, doing various manipulations on them. And of course, we use NumPy to represent the differential equations and the routines for computing this cell refinement, as I'll mention in a moment. So what exists right now? And there are two things I'm going to mention. There's really not much more than that. This first thing isn't even a tool. It's actually a wiki, the Hybrid System Tools Wiki, which is an index for various things that would be like TuLiP. It's hosted at UPenn. And if you go there, what you'll find is most things are written in C, C++, Java, kind of an offensive amount is in MATLAB, and it's not clear whether those would work in Octave. And what's worse is a lot of these tools have licenses that are not open, and so really you can't do much with them unless you start paying a premium. And so this wiki didn't really take off. The community didn't adopt it. This is an issue I think everyone deals with here in your own scientific communities. What does it take for people to publish a paper and release code and release a way to reproduce what they did with the code, so access to data and so on? In the hybrid systems context, what often happens is that people write a quick implementation of an algorithm to generate plots for a paper. It's nice, and maybe they can prove results about the algorithm, like correctness or convergence or soundness, other notions of algorithms. And the paper's published, but there's no code to reproduce it, and if you ask the author for it, then you'll get it, but it's just some nightmarish tarball of MATLAB scripts. And in many cases, when the code is released publicly, it really isn't much more than a few MATLAB scripts, and so it's not particularly useful in your own project unless you're going to have that tied. So that was just a comment about why I don't think that index really took off. And there are no other major tools to speak of that are trying to create this setting that TuLiP is, except this is a similar one called LTL MOP. MOP is supposed to be mission planning, sort of a buzz term in that robotics community. But it's developed by ScottC.Livingston and her students at Cornell. And unlike TuLiP, it's targeted specifically at planar mobile robots. So in the previous slide, I had a task that was defined in terms of rooms. And that doesn't have to be the case necessarily in TuLiP. You can define polytopes or regions of arbitrary dimensional spaces, literally, and have specifications defined over them. In LTL MOP, they're looking specifically at planar robots, which means you would draw a rectangle and say this is the room. And here's another region, another rectangle that I want to go to before that room. And so their whole semantics is centered around this planar mobile robots. That's entirely in Python too. So, whereas previously I said most tools are not in Python, mostly MATLAB or Java. In fact, LTMOP is in Python, so that's a plus for it, but it just doesn't address a very large problem area. And one thing that is nice about it is it has a nice visualization routine for counter strategies, which means sometimes you can define a task in the way that I did, but it's actually not satisfiable, as in there's no controller to actually implement it, to make the robot do something. And so they have a way to visualize that that's actually fairly nice. So what are some of the pieces of TuLiP? I'll talk about the first two modules in a moment, because I think those are of the most general interest to people in the audience. There's one for discretization. Discretization means given this initial partition defined in terms of your task, like at the level of rooms, refine it somehow, given the dynamics, so that you can then steer the vehicle in this way among the cells that I referred to before. So discretization implements some methods for doing that. Automaton defines an automaton class and lots of stuff to go with it, essentially to represent these decision-making procedures that implement a strategy for following the specification. So I realize there's some danger that I'm just using lots of terms and no one has any idea what I'm talking about, but because there's no feedback, I'll never know. So I'll reiterate. The automaton is this solution to the temporal logic formula, which describes what you want to happen in terms of a task. The automaton interacts with the continuous system, so it sends commands, go from this cell to this cell. And the continuous state controller will actually implement it by applying torque to the motors and driving through. So that's the hybrid nature of it. Also, TuLiP provides an XML file for saving, reading, writing your results, and an interface to a graph visualization tool called Gephi. Has anyone heard of that before? Okay. Oh, cool. Well, so some of these automata that we produce have thousands of nodes, and just dumping it to dot and using graphviz really doesn't cut it. And so the tool we've come to use is Gephi. It's a Python conference, and Gephi's not Python, but if you have alternatives that you'd like to refer me to, I'd like to hear it. And also, TuLiP provides some wrappers around some synthesis tools, which tend to be written in C or Java. So let's look at a specific example to make this a little more concrete. With TuLiP, you can define a problem like this. So here's a 2x3 grid where the task, roughly speaking, and this example is all in the repository, so you can run it later and see the precise details, but roughly the task is to steer your vehicle to the upper right cell, and to always be doing that. And if you receive some kind of non-deterministic flag, then you have to go to the lower left cell. And so that's the task level description. This is actually a continuous space. It's a subset of the plane. And you have dynamics which have drift, which means if you're not applying control input, then if you're not at the lower left corner of the space, then you begin to drift away. And the farther you are away, the faster you drift. So constructing a solution with TuLiP leads to refinement of the partition. So on the right, we see these two cells were refined. They're so far away from the origin that the drift is so large, combined with the control input bounds, that you have to actually look at smaller cells in order to satisfy that reachability property. And that is automatically done. So then we just see a trace of a simulation that runs through a strategy implementation by the automaton, and then it drives the continuous system. So I won't spend much more time on it. For the sake of time, this is probably a more general interest, the Polytube module. So before we began, I didn't know if there are any decent Polytube computation modules in Python, and that was the reason why there was initial dependency in MATLAB. We've since broken from that, and there is some nice code in TuLiP for working with Polytube. So what is a Polytube? Convex bounded. You can think of it as a polygon. And it turns out that you can represent it two ways, as a convex hull of finitely many vertices, or as half spaces. And also, I think this is the only theorem to be mentioned at the conference. But it's an important result, and basically a problem that you get when you're working with polytopes is mapping between these two representations. And so those exist in TuLiP. It's called the Polytope module. Actually, it's a sub-package. And you can do fairly standard things with it. I'll just keep plugging along for the sake of time, but here are a few lines of code at the bottom, basically two import statements to get access to the Polytope routines, and then another one to get the plotting function. And we use NumPy to generate random points in the unit square, 5 of them, and we take the convex hull of it. Actually, the algorithm is called quick hull or Q hull, and then you can plot it. And so NumPy and SciPy are used underneath, and Matplotlib is used for all the plotting. And on the right, we can see I just repeated this operation 4 times to get 4 polytopes. And there's also a Goodworld module, and the printing functionality is not very good in it. Right now, it's mostly ASCII art, as you see on the right. Goodworld's come up in a lot of places, so in that basic sense, it's not a particularly strong contribution. It's useful in this context because if you're doing research in hybrid systems, you want to be able to map from a discrete problem, discrete representation like a Goodworld, into some kind of continuous space. And so there are routines for doing that, both for representing the grid world and then embedding it in a continuous space, and also mapping the grid world description of a problem in terms of static obstacles and other things like you see on the right, in terms of a temporal logic specification, and that can be done automatically. And so there's 2 lines of code, and basically you import the module and then you can just generate the random grid world. Looking back, this began as an implementation of a particular method for someone's PhD thesis. And at that point, I suspect most code dies or it gets hidden away on some hard drive. But this one has evolved into this framework for hybrid systems research, largely because there are a couple of grad students, including myself, who picked it up. And now what basically happens, so it's a young project, so I can't like talk as if there's a big history, but now each summer there's some undergraduates who work on some project in the lab and they'll push whatever they do into TuLiP, which means it's growing. And also it serves as this context where the students can put their algorithms that they publish and write papers about and provide reference implementations in TuLiP, including example code to run it. So I already mentioned those things. And so looking forward, these are promotional items for discussion, and you can just approach me after the talk if you have interesting ideas. I have some opinions on them. I think they're items that come up for anyone who's working on software projects. The first one's kind of dull, I suppose, or should be obvious. The issue that I bump against is that I work with a lot of people who do almost exclusively theoretical work, which means when they write code, it can be sometimes a nightmare to work with and to debug and so on. The other issue is once you've already jumped this gap that has been referred to in other talks where you get people, researchers to start using Git in their workflow, start using IPython notebook, how do you get them to write good documentation to go with it? So a social engineering question. Because if you have the code that can reproduce the result, then isn't that enough for the reproducibility? But it's not necessarily, or it can be a lot of work to back out the meaning of code. These are some internal issues I'm going to skip for the sake of time. And so here's something that might come up for those of you who are working in an academic setting. How do you deal with feature creep and maintain coherency over a project? So I've tried to sketch out why TuLiP might be this nice setting for working with hybrid systems problems. You can represent polytopes and work with them fairly easily. You can describe the continuous aspects of a problem and this formal temporal logic specification level of a problem. But there's a danger that everyone wants to put their little bit into it. And that's what feature creep is. So how to deal with it. So far, we really haven't been dealing with it. We've just been trying to keep the style of the code clean and letting everything grow. But it's not a big enough project yet where this has become an issue. And the last one I already alluded to, so I guess I'm mostly out of time anyway. So there's a URL. So this is probably the first project we mentioned that's on SourceForge. That's my inheritance. I use GitHub mostly otherwise. But it's there. And that's my email address. And this work is supported by the Air Force Office of Scientific Research, Music, and the Boeing Company. So thank you for your time, and I'll take questions.
We have time for maybe one or two questions if there's any in the audience. So I think your last slide on looking, we can go to the mic. Yeah. I think your last slide, I think there's something that all young projects wrestle with all these things all the time, so.
Yeah, well, so this is my first iPad. I didn't really know what the talk should be ultimately. I mean, I submitted an abstract and I thought this should just be a tool talk, but when I've come here, it seems like the theme is more so engineering questions, as in how to work with projects, so.
Sorry, my question is, how much of you guys actually use this for kind of classic control theory problems, like, for example, like a motion controller where you can try to maintain position with, outside of what the polytope stuff that you're doing?
Yeah, we don't. And, okay. But there is a Python toolbox, or I don't know what, the toolbox word comes from MATLAB, sort of this abomination of a word that's carried over, but there's a Python package for control that's developed by the same group called Python Control. Mm-hmm. And there's no time to talk about that, but that actually implements a lot of these basic methods. So, for example, LQR controller. Do you have a traditional control theory background?
Actually, on telecom, PLL kind of stuff.
Cool. Well, Python control has these methods for like frequency domain analysis of systems and so on, time domain, mapping between the two, Kalman filtering. I guess everyone has a Kalman filter these days, but there's LQR controllers and so on, but that's a different thing. So look on SourceForge, Python-control. Okay. And there's some push to try to make that more of a legitimate scikits kind of thing, but that's only within people who are doing control theory research, and so almost no one in the physical sciences has heard about it.
All right, let's take our speaker again.